Commissioning a substation requires a rigorous 41 test sequence to prove an isolated digital relay software system can perfectly control the high-energy analog grid. This process ensures the digital interface will correctly command the massive copper hardware behind it during a lethal fault. Governance for these test parameters follows a strict hierarchy. When international standards from the IEC, IEEE, or NEMA conflict with a manufacturer's specific instructions, technicians are legally bound to apply the single most stringent approved parameter. If a global standard allows a response in 50 milliseconds, but the panel manufacturer requires 40, 40 becomes the absolute law. Before any physical testing begins, engineers establish a secure pre-flight boundary. This involves bleeding off stray capacitance with proper grounding, equipping arc flash-rated personal protective equipment, and securing a mandatory 5-step lockout-tagout, or LOTO, perimeter. Mechanical isolation follows. Technicians insert highly engineered test plugs directly into the relay to sever the connection to the external grid. This action simultaneously shorts all unused current transformer, or CT, circuits. Because an open CT circuit on a live system generates lethal secondary voltages, this physical shorting is a non-negotiable safety mechanism. Only after locking down the physical boundary and isolating the workspace from the analog grid is the environment considered ready for secondary current injection. Every single module in the 41 test commissioning framework follows the universal test algorithm, a mandatory 7-step operational procedure. Steps 1 and 2, verify and isolate, involve loading approved engineering setting files and verifying internal logic checksums. This mathematical algorithm ensures that the relay's configuration code remains uncorrupted. Once the data is confirmed, the team applies LOTO and verifies the isolation of all outputs. Steps 3 and 4 are connect and inject. Technicians wire a calibrated secondary injection test set, multimeters, and binary input-output leads to the isolated terminals. They then inject controlled secondary currents to test the relay's performance against specific characteristic bounds. Step 5 is confirming logic. As the injection set pushes the relay past its thresholds, technicians verify that the unit accurately toggles trip contacts, engages mechanical lockout paths, and triggers the substation automation system enunciation with an accurate timestamp. Finally, steps 6 and 7 execute restoration and recording. The team removes the test blocks, normalizes the physical shorting links, confirms no active alarms remain, and captures all final test values for formal witness sign-off. This uniform 7-step protocol serves as the operational engine for the commissioning process, ensuring absolute repeatability and safety across all 41 distinct protection schemes. Phase A focuses on differential protection, designated as Relay 87. These modules operate on Kirchhoff's current law, which requires that the current entering a healthy zone must precisely equal the current leaving it. Any missing current indicates an internal fault leaking to ground. This commissioning schematic for line and cable differential shows the testing setup. Technicians use the secondary test set to inject current into just one side of the simulated zone. This creates an imbalance to locate the precise pickup point where the relay identifies a fault and issues a trip command. To pass, the measured pickup and dropout characteristics must map perfectly onto the approved slope diagram, validating exact resetting ratios for different curve profiles. Transformer differential testing adds a layer of complexity. Because powering up a transformer draws a massive, unbalanced inrush current, technicians must inject secondary and fifth harmonics during testing. This proves the relay's logic will recognize the harmonic signature of an inrush and successfully block a false trip. Busbars and reactors require both stability and sensitivity tests. As shown in this primary injection diagram, the team must push massive primary test currents through the actual high-voltage conductors, using phase angle meters and clamp meters to verify the full physical circuit. The expected behavior is twofold. During the external stability test, the relay must ignore a massive fault current passing through the zone. During the internal sensitivity test, an injected fault inside the zone must yield an immediate trip. Spatial protection forms the unyielding perimeter of grid defense, validating physical boundaries before localized anomalies are considered. Phase B moves to localized node monitors, directional overcurrent, or 67, and directional earth faults, or 67N. These relays analyze specific vectors rather than strictly bounded zones. This schematic details the procedure for a 67 relay. Technicians must simultaneously simulate current magnitude and a polarizing reference voltage. By comparing the two, the relay calculates the phase angle to determine the exact direction of the fault. The acceptance criteria require the injection set to push the phase angle through forward, reverse, and undefined zones. The relay must trip or block as mapped on its inverse time curves, isolating faults downstream while ignoring currents feeding back into the grid. In this restricted earth fault schematic, we observe the sensitivity test. Technicians physically swap the polarity on a single current transformer circuit to force a calculated unbalance. This proves the relay will detect a low-magnitude earth fault near the neutral point of a star winding. These localized tests prove the relay acts as a targeted, intelligent first responder. The unit performs continuous vector math to selectively and surgically remove hazards. Phase C covers distance and impedance protection, or Code 21. These relays calculate fault distance by dividing voltage by current to find the apparent impedance, plotting the results across defined protection zones on an RX plane. Guarding transmission lines that stretch for hundreds of miles requires synchronized equipment. Technicians link their injection sets with GPS time synchronization kits to maintain microsecond accuracy between substations separated by vast distances. This schematic visualizes the teleprotection logic test. By tracking digital signal propagation between Substation 1 and Substation 2, technicians verify the echo-only and echo and trip logic gates. The expected behavior validates the carrier's send and receive capabilities. The injected fault must trigger the required blocking sequence, with event recorder timestamps aligning perfectly across the geographic gap. Impedance testing elevates the commissioning protocol into a cohesive, grid-scale communication network, ensuring distant substations operate in perfect mathematical harmony. The final phase analyzes the grid's time-domain safety nets, which are engineered to manage mechanical breakdowns and govern automated recovery. The upper half of this logic diagram maps the auto-recloser sequence. Technicians test exact timings, verifying the required dead time before a closing pulse and the subsequent reclaim time before the line is officially declared restored. The bottom half displays the circuit breaker fail logic. Technicians simulate a scenario where a mechanical trip initiates, but the injection set continues feeding current. The logic must recognize the breaker is stuck, triggering a timer to execute a backup trip to all adjacent breakers. Once a fault is cleared, the system must reconnect. Synchronism check, or 25 relay testing, prevents mechanical shock to the generators by mathematically aligning grid sections before permitting a re-energizing close command. To test this, technicians inject live line and live bus voltages into the relay. They alter the magnitude, frequency, and phase angle to pinpoint the narrow window of alignment that permits a close and the specific boundaries that block it. These fail-safe tests prove the grid possesses the autonomous logic to heal itself, bridging the gap between routine faults and cascading hardware failure. A successful secondary injection test confirms the digital logic is correct, but a passed software test does not mean the panel is ready. The physical layer, copper wires, terminal blocks, and mechanical coils, will eventually subvert the code. Ghost currents are a common edge case. When an otherwise perfect relay calculates incorrect vector math, the cause is rarely a firmware glitch. It is typically artificial resistance introduced by a loose terminal connection or a frayed copper test lead warping the injection path. Similarly, a flashing trip circuit supervision alarm requires active tracing. Technicians must pull the schematics and follow the DC supply wiring point to point, checking for blown fuses or degraded trip coils on the physical breaker mechanism. Commissioning engineers must trust their first principles. When digital results don't match the raw physics of the panel, the physical layer is almost always the culprit. Every testing script terminates at the hold point, the final gate requiring verification from client and operations witnesses before the unit is deemed safe for service. The shutdown procedure is meticulous. Technicians must pull the test plugs, normalize the shorted CT circuits back to an active state, reclose the physical trip links, and clear any lingering alarms from the substation automation system. Commissioning requires the deliberate, destructive isolation of the protection relay. The mission is only successful once that isolated digital brain is flawlessly reintegrated into the live operational grid.